Well, hey there, mathletes. Here we are starting 6.1. It's exponential growth and decay functions. So the first thing we want to understand is what is an exponential model, or what does exponential growth mean? So you can identify exponential growth if we look at a table of values. And if our output are y values, if we take those values and divide them by each other, so if we just took like a1 divided by a0, or a5 divided by a4, okay, we should get a common ratio, meaning that every time that there's a common number multiplier, okay, that would get us to our next term. So this is what we call an exponential model. Okay. So classic example here is dealing with money in a savings account. So if we look at this account and we have the amount of money that we have after each year after it's been in a savings account. So if we want to know what kind of interest it's creating, okay, we can take these successive values. So 1040 divided by 1,000, we get 1.04. 1081.6 divided by 1080, we get 1.04. So notice the pattern emerging. Okay, and as we continue down and look at all these successive ratios of 12,000 or 1,216.65 dividing by 1,169.86, we get 1.04 well. So that's our rate of change, our constant multiplier. Okay, so then that ratio, if we put into an equation, we take that initial value that we started with and have this as 1.04, our R value, okay, and T being the time in years, we'd be able to use this model to figure out how much money we would have in 10 years. Okay. So as we're looking at these functions, this is kind of our parent functions that we really want to be familiar with by the end of this lesson. Okay. So X is going to be our input, our domain, and it's going to be a real number. Okay. When we're talking about initial values, that's our A value. Okay, we're not going to let that initial value be 0. Okay, we got to start off somewhere. So if we're talking about a population, we don't start off with a population of 0. We usually start off with something. Okay, same thing with money. If we're going to put money into a banking account, if we put 0 into it, it's not exponential growth. Okay, we have to start something with growth. Okay, our B values, we're not going to worry about B values being negative, but we're only going to really be concerned when B values are positive. Okay, and B can't be equal to 1, because if B is equal to 1, then we don't have a growth happening. Okay, that rate of change is 1, so you're just getting the same value over time. Okay, so that B value, we can also think of that as our R value, or our common ratio between our terms. So if we looked at this graph, okay, as this 2 times 3 to the x, okay, and we were graphing this, the first point I'm always going to graph is my initial value at 0, which is 2. That comes from my A. And then my next points just come from multiplying. Okay, so what's 2 times 3? Well, that's 6. So that's 2 to the third. Okay, the next one, if I want to know what 2 times 3 to the second is, well, that represents 2 times 3 times 3 again. Well, we know this from the previous one was 6. 6 times 3 is 18. So then we'd be way up here for our next one. So we kind of get this graph that goes this way. And then if we want to go backwards, well, what's the backwards of multiplying by 3? Would divide by 3. So 2 divided by 3 is about 0.6. It's 0.6 repeating. So then here, if we go backwards at -1, we'd be at about 0.6. So we get this graph. So then you keep dividing things by 3, you're never going to get less than 0. It's never going to drop down to be negative, but you'll get very close to 0. And we'll talk about what it means to be very close to 0 in a second. Okay. So we're going to have kind of two families of functions here. We're going to have growth functions and we have decay functions. Growth functions are going to happen when that rate of change, that B value, is greater than 1. It's a positive growth. Okay. So if we look at an example here, when we have using Desmos, Okay? If we have a value of being 1, initial condition, so our graph, we're right there at 1, and our growth is 2, we're doubling each time. Okay? So notice, if we want to flatten that curve, okay, that growth rate, we want to dwindle and have that growth rate be smaller. But once that growth rate becomes less than 1, notice how the graph changes. We end up getting a graph that represents decay, and its things are getting smaller. It's a decreasing graph. But when that b value is larger than 1, we have things that are growing. Okay? So as we're going back to our slides, we can see when that b value is greater than 1, okay, it's a growth factor. So we see that this is 2 is greater than 1, so it's growth. If that b value is between 0 and a 1, again, b is not going to be negative. Okay? It's going to represent decay. Okay, so like 0.5, 1/2. That means every time successively you're cutting down your values by half of what it was before. So you get a decay. Okay. So a core concept here is this idea of asymptotes. You see that word right there. An asymptote is what I was referring to as we got closer and closer to 0. So if we think as this being a growth function, okay, notice our b value is greater than 1, it's increasing, and so it's every time as we go across, we're multiplying by another b value, and it's getting exponentially larger. Okay, well, if we go this way, the opposite of multiplication is division. So if we take 1 and divide it by b, our next point over here is 1 over b. And then the next point is going to be 1 over b divided by b again. And that value is going to get smaller and smaller and smaller. It will never get to 0. So what we call that line that it gets very close to is an asymptote. Often I'll graph it, and usually I'll do a dashed line at 0. Okay, to represent that it gets so close and gets closer and closer each time, but it will never necessarily cross that graph, but it gets very, very close to that graph. Okay, when we talk about growth functions, our domain is all real numbers. Okay, and our range, notice, is always going to be greater than whatever our asymptote is here. Okay, so notice for most of our functions, it's going to be 0. So y is greater than 0. Notice it's non-inclusive because you can never be equal to 0 if you keep dividing something, let's say, in half, right? You'll always have something left over. Okay. The other side of the coin is our decay function. Okay. So as we're decaying, we're going to notice that things are getting smaller and smaller, and dividing by b each time as we go to the right now. Okay, so we still have a range of y being greater than 0 and a domain of all real numbers. Okay, but we get that asymptote there on the x-axis, or that equation y equals 0 of a line, which is there. Okay. So if I want to graph these functions, okay, I'm typically going to start off by graphing my asymptote. I like to graph my asymptote as a dotted line, so it represents it's not actually part of the function. Okay, so on this one, my initial value is 2. Okay. So we should have at least 3 graphs, points on our graph as we're graphing. So what's 2 times 4? Well, that's 8. So there's 1 point. And now going the other way, what's 2 divided by 4? Well, that's 1/2. So that is 1/2. Actually, it's a bit lower right there. Okay. So as I graph now, I see that I get something that looks like that. Okay, it's kind of a swoosh there. Okay. Notice sometimes that negative, so think of this as if you plugged it in. So 2 to the 4th to the -1. Okay. Well, that's equivalent to saying, well, that's 2 to the 4th to the 1st power, because a negative exponent makes it into the denominator, and 2 divided by 4 is 1/2. So we see why that division happens there. Okay. Now 2 to the 1/4, I'm going to expect a decay because I have a b value that's less than 1. So again, I'm going to start and graph my initial value, 2. Okay. So my next, I multiply by 1/4, and 1/4 of 2 is 1/2. So notice I'm here. Okay. And if I go the opposite of division, I can multiply. And multiplying by 4, I'm going to get 8 this way. So you see that there's a reflection happening between these two graphs. Okay. So when we have the reciprocal here of this d value, there are reflections of each other. One representing growth, one representing decay. So without graphing these, I should be able to represent and say, all right, this value is greater than 1, so it's growth. So there's an absence, there is no a value here, or we can imagine it as a 1 times 2. Okay, it's not a 0, okay, but a 1. So we have a 1 there, and then our growth is times 2, times 2, times 2, and we have a graph like this. Again, be mindful of your asymptote. We shouldn't cross the axes. Okay, here again we have a b value that is less than 1. Okay, so that is a decay. And then I can graph again. My a value is not, it's present as a 1 but not written. Okay, so I start there at 1. I'm going to be a half this way. Half of a half is a fourth. Other way I multiply, so 2, 4, 8. Notice I get my decay graph. Again, a reflection of the previous graph. Okay, so some course concepts that we want to think of, again, is thinking about our b value. So that a value in our graph, we can identify that point, that y-intercept. Okay, whether it's growth or decay. Okay. If we get an a value that's negative, we'll be down here. We don't see that very often with our models, but we can do that with our graphs. And in transition, thinking about a b value that is between 0 and 1, it's a decay. We still have the asymptote or the intercept at 0, a here as well. Okay. So when we're talking about these growth functions, this is kind of our parent function growth function, okay, where our final amount that we have is our y, our initial amount is a, that rate of growth, okay, that r is going to be in your decimal form, p is time, and this is your growth factor. So your growth factor is b. B is not necessarily equal to r, okay, but they're in relationship between these two. Okay, so you'll see what I mean here in a minute. Okay, so if I want to determine whether each function represents a growth or exponential decay, now I'm looking again, and I want to identify the percent or the rate change. Okay, so this number is greater than 1, and you can always, if you do whatever that value is, okay, that growth factor, and you subtract it to 1, if it's positive, okay, it's a growth. And this is the rate. So the growth is by 0.07. And as a percentage, because often it's reported as a percentage, we move our decimal place 2 over. So that's a 7% growth. Okay. So over here, we can see that if we take our growth factor there, and we subtract it from 1, 0.02. Notice 0.02 is negative, so that is a decay. You're expecting that because it's less than 1. And that decay factor, again, 2 decimal places, is 2% decay. We don't say it's negative. The decay implies the negative. Okay, so as we're looking at population growth, populations often grow exponentially, whether we're talking about bacteria in a petri dish or a population of people or animals. Okay, so in 2000, the annual growth rate was 1.2 1.24% in the US. We can use that to write a function, okay, to model the growth in millions. So this is after the year 2000. Okay, so if we notice our growth, so our growth rate is 1.24. Our initial population, okay, we're going to let 2000 be the year zero. Okay, so in the year zero, there's 281 million. So that is my A value. Okay, and we're doing it in millions. So we're going to say that 281 times, okay, my growth factor again is 1 plus my rate of growth. My rate, I want to write it as a decimal, so move it over 1, 2 decimal places, fill in zeros if need be. So 0.0124. Okay, so that ends up being 1.0124. And that's my growth factor. Okay, that is going to be raised now to the time in years. So it's just X. And so that's how we can predict our growth. Okay, so I went ahead and typed it in for our year of 2020, one that won't be soon forgotten. Okay, and so after 2020 would be 20 years since 2000. So if you plug in 20 into this to get a model, okay, so I do 281 times 1.0124 to the 20th power, I get f of 20 being equal to 359.5 million in the US. So let's see how well that this problem identified our growth. So I went ahead and Googled our growth. And you can see we're at 328.2 million. So not too far off for a model that was using data from 20 years ago. So you can imagine we actually flattened our curve with our population growth. And so you could hypothesize that some of the reasons why that growth curve was flattened. And so one prediction might be just with newer generations, there's probably less people having children. A lot of young couples are deciding to be without kids or just waiting longer to have kids. So might be one reason that the growth rate slowed down in the U.S. Okay, so when we're talking about our next example, depreciation. So I'm going to use a classic example of the car. The car is one of the worst investments you can make for trying to get your money back. It can be a great investment if it's a way that you make money, meaning you get it to work and you get it's a way to make income, but you're not going to get money back out. Okay, so if we look at an initial car was valued at $20,000. After 1 year, the value of the car is about $17,000. Okay, there's all sorts of apps and places online that you can look up cars and find values of their car. Okay, so we can write an exponential function to model this situation. Okay, and we want to find that value of the car after 6 years. Okay, just find our growth rate. Okay, we want to be able to find our R value. So to find our R value, we're going to take our final value. Okay, so that was 17,000. Let's get a better color here. Subtract our initial value over our initial value, and we're going to see that we get what, negative 3,000 over 20, or reduces to negative 3 over 20, which is negative 0.15. So since it's negative, it's a decay of 15%. Okay, so that's my R value. So notice my B value for my equation up here to fill in is going to be 1 minus, because it's a decay of 0.15. Okay, and you get 0.85. Another way you can think about this is if you want to just find your B value, remember that's your successive ratio. So if you did, if you just do 17,000 divided by 20,000, you get 0.85. Okay, so our function here, so let's just do the value of our car. So we're going to do S of X. Well, the initial value of the car was 20,000. Our growth rate was 0.85, or decay, and we want to find it after 6 years. So S of 6, using my calculator, I can see that after 6 years, this car is now only valued at 7,542.99. So that's dollars. Okay, so you can see cars go down in value quite a bit over time. So one of our favorite topics we like to talk about is money. So that's one of the most important things for us to be looking at exponential models, whether you're investing money and wanting to get a rate out of your money, or if you're asking to borrow money from a bank, you're going to get a rate that you're going to have to pay back in interest. So either way, it's important to understand the financial implications of exponential growth and decay. Okay, so our normal function here is A, where A is the amount in the account at the end. Okay, P is your principal that you deposited in the account, or the initial amount. Okay, R is going to be your rate, okay, expressed as a decimal, not a percentage. Okay, and N is how often it's compounded per year. So depending on the wording of the problem, so if it's compounded quarterly, that N is equal to 4. Okay, if it's compounded daily, right, N would be equal to 365. Okay, if it's monthly, N would be equal to 12, and so on. Okay, and the final one we can see is our T, which is our time. Okay, so if we deposit $9,000 into our account, okay, that is our principal. Okay, so then I have 1 plus my rate that the bank's giving me is 1.46% annual interest. So that as a decimal, so 1, 2 over is 0.0146, and don't round those, divided by our N. Our N is compounded quarterly, so that's a 4. Okay, and I want to find, and then I have to do 4 again, so the N, notice, appears twice, and then that power is multiplied by how many years that we want to find the balance. So after 3 years, how much will we have in this account? So I like to simplify things first before I put them into the calculator. So I get 9,000. If I do 1 plus 0.0146 divided by 4, I get my growth factor, which is my B value, 0.00365, and 4 times 3 is 12. So as I put that into my equation, I see that after 3 years, I'll get $9,402.21. Okay, not a bad way to make money. Just have your money make money by putting things into savings. Okay, that concludes our notes for tonight. Please highlight any questions you have and bring them to office hours.